Okay, so I'm going to talk about NTP and Rust, and spoiler alert, I'm not going to talk too much about NTP. I'm primarily going to be focusing on why we chose for Rust to implement this, and some of the benefits it gives us, particularly around testing and fuzz testing. So, who am I? I am David. I'm a software developer at Tweede. I have a background in physics and mathematics, and I've been working on NTP for ISRG's Proximo project now for a little over half a year, building the NTPD RS project. What we're going to talk about today, I want to talk a little bit about what NTP is for those who don't know it, how it works. We'll keep this very high level. We won't go into depth. If you want me to talk in depth about NTP, I can. Just talk to me afterwards. Because otherwise this won't fit in half an hour. Then why Rust? Of course, most of us here will have an answer to that, but it's good to go over that for a short while. And then we're going to do a deep dive into fuzzing. I'm going to talk a little bit about the source code of NTPDRS, and I'm going to show how we use fuzzing, what we do with it, and what kind of benefits it gives us. Okay, so what is NTP? NTP is used to synchronize clocks over the internet. It is, at its core, that's what it's supposed to do. If you have a laptop, if you have a phone, your router at home, it needs to get its time from somewhere. NTP is how it gets that time. So on the internet, there are a couple of what we call Stratum 1 servers. These are servers that get their time from somewhere that's not the internet. This can be something like a GPS receiver. It's very common, but it also, standards institutes have usually these clocks they use to keep UTC time, and they also provide access to that over the internet via NTP. So these are those servers. Then there are a lot of servers out there on the internet that just themselves talk to these higher level servers or other time servers on the internet, keep a copy of the time locally, and then distribute that on. It's done primarily to do a lot of load balancing, because there's a lot of people who want to know the time. So having a lot of places where you can get it. And then there's clients that can ask all these servers. What's important to note up front is that a client can get time from multiple servers, typically will. Gives you a little bit of resistance against if one server is completely in the weeds and doesn't understand what time is anymore. This happens more than you would think. It is hierarchical, but it's more like a directed acyclic graph. It's not really a tree structure. So you can hang your client to servers at all levels in this hierarchy, and it's going to work just fine. So how do we do the time synchronization? In its essence, it's very simple. A client sends a request to a server, hey, what is your current time? And the server answers. But instead of answering with just a single timestamp, what the server does, it keeps a record of when did the time packet arrive, that was the request, and when did it send the response, and those two timestamps it sends with the response. And then if the client can also keep when it sent its request and when it receives its response, then we can make a simple assumption, namely that going from the client to the server takes about the same amount of time as going back. This is not entirely true over the internet, but it's a decent enough approximation that it usually works, and you can't really do better. And then with a bit of math, the client can work out what the time difference is between what it measures as time and what the server sees as its current time, and then it can correct for that or do with that whatever it wants. So then you usually do this for multiple servers. You do a bit of further math, check which servers are compatible with each other. Do they all give you the same time? Is there only one outlier, or are they all over the place? And maybe we shouldn't be synchronizing to anyone at that time. And then combining all that information, your NTP client will at some point make a decision. Okay, I need to adjust my clock 1 second forward. I need to adjust it 5 milliseconds backwards, whatever. So that on a very high level is what NTP is and does. So why do we want to re-implement this in Rust? Well, let's first take a look at current implementations. There's 3 major implementations of NTP. I say major, I mean with that is that they implement both the client side of the protocol, so they do the full synchronization and they do that over time, as well as being able to be a server and provide time to further clients. There's the reference implementation. For quite a number of years, this was the only implementation of NTP. It's implemented in C. I've looked at the source code. I wouldn't recommend it. It has a reputation for having a lot of security issues, both in terms of amplification attack potential, in terms of memory safety issues. It is not the greatest implementation in the world, in my view. There's NTP-sec. It's a fork of NTP, of the reference implementation. It's starting to move some of the code to Python, which helps with memory safety, but most of it is still in C, and I think they're planning to keep all the performance-sensitive stuff, which is most of the packet parsing, they plan to keep in C, as far as I am aware. It is, because it's a stripped-down version, it's a bit more focused on security. It has implemented NTS, which is an authentication layer on top of NTP. So it is a little bit more secure, but it still has fundamentally a lot of the same issues that the reference implementation has. And then there's Crony. Crony is actually a fairly modern implementation, still written in C. It has had memory issues in the past, but it seems to be written a lot better than the reference implementation. It's essentially a complete implementation from scratch. So that's also, by the way, what our NTPD RS implementation is. It's not a C to Rust port. It's completely built from scratch in Rust. So why do we choose Rust? Well, obviously memory safety. Memory safety is like the selling feature for Rust, but it's not the only selling feature for Rust, and there's a lot of other benefits that Rust is actually giving us day to day in implementing this project. One, type safety. The Rust type system is really expressive, and it turns out to be really useful for NTP to be able to say these states are invalid, so we don't even make them representable in the type system. It saves you a lot of headaches and bugs down the line, turns out. Dependency management. NTP is slowly becoming a little bit more complicated. There's a layer called NTS, which is a security layer on top of NTP that requires a lot of crypto to be implemented as well. And it's really nice to have just easy ways of importing that and managing the dependencies for that. We've got easy integrated testing support. Writing tests it's a breeze. If you've ever written tests for C code, testing frameworks for C, I'm not the biggest fan of them, and having just what Rust provides is just, it's so much better. And interestingly, it also provides very good fuzzing tools. And this is what I want to focus the rest of this talk on, is fuzzing tools. It's not something that people commonly use these days, even for many Rust projects, even though the tooling is really there. But it can give you quite a bit more than just normal testing. So let's go into that. So what is fuzzing? At its most reductive simplest, fuzzing is basically testing your code with random inputs. We just throw random stuff at it and see what it does. Typically, in the way that people know this, it's used to find crashes, memory safety bugs. Well, not so much in Rust, but if you use unsafe code, you can still find them this way. Panics, just your code misbehaving in gross ways. However, it turns out, and our experience has been very positive with this, is that you can also use it to test invariants of your code. So if you have a bit of code that needs to encode or decode something, or you have two functions that should be each other's inverse, you can use fuzzing to test those properties. So it's useful for all sorts of things. We use it to check for example, our parsing code, but we also use it to property test algorithms, data structures, do things behave the way we expect them to, that sort of thing. So what does Rust provide for this? Well, there's Cargo Fuzz. It's not built into Cargo itself. It's a extension. But it's really easy to install. It's just a simple cargo install. If you have a new project or you want to set this up in, it's really simple. Just cargo fuzz in it and basically set up everything for you, including an example. Not quite this example. This one I've included with a bit of reason. We'll get into in a minute. And then you just can simply run your fuzz test with... Oh, I missed a fuzz here. I'll correct that for the PDFs that are going to be online later. You can basically run it with cargo, fuzz, run things. It needs the nightly compiler. It needs this because it needs to use a number of sanitizers in LLVM, and those are only available in nightly. But it's only a testing thing. You can still just compile your code with a normal stable compiler. It's not much of a problem. So what does a typical fuzzer test look like? Well, it's basically a simple file with some code in it. We use fuzz target instead of main. And fuzz target basically describes what do we want to test. We say we want some input. In this case, we want 2 integers of just the machine type size. And then we have some code that we're going to test. So this code has a bug, this code under test here. Can anybody spot what the bug is? Correct. That was quicker than I was expecting. It's a bit subtle, but this code can overflow. People tend to forget that addition might do that. So if you run this, it'll find that this can overflow. Then let's go to a little bit more the practical examples, so what we use in NTPD RS. So one of the things we do is, I need to zoom in. There we go. Is this readable? So this is, for NTP, we need to parse these network packets. And we need to be able to serialize them. Deserialize and serialize here are the functions that do that. So this is a fairly unstructured test. We just take a vector of bytes. Just any bytes will do for this purpose. We check, is this a valid NTP packet that we can parse? This shouldn't crash, but it is allowed to give us an error because not every sequence of bytes is a valid NTP packet. If it is, it turns out that a property of the way we parse our NTP packets is that it's symmetric. So a deserialize followed by a serialize should give the exact same sequence of bytes. So we also do an immediate assert that that is true. So this exercises our packet parser in ways we never would have done ourselves. Turns out that the packet parsing for NTP is not that complicated, so this has not yet found us bugs. But I do have another example, which is a bit more interesting, and that is IP filtering. So this is a bit of a larger file. I'll go through it in several parts. Let's start with the main fuzzing target. So one of the nice things that Cargo Fuzz gives us is the option to actually not test just with a random byte vector, but it can provide us random structured data. So in this case, I say I want some IP subnet specifications, and I want some IP addresses, and just give me 2 lists of those, and I'm going to use those to test my code. And if you provided ways to generate that, I'll go into how to do that for a little bit later. It'll just generate those for you. I'll do that in a clever way that the fuzzer will know how to mutate these things. In our case, we use that to test something that is called an IP filter. So what we do in our server-side code is you may not want everyone on the internet to be able to ask things of your server. So we have functionality that allows you to blacklist IP addresses or subnets of IP addresses. This blocklist checking needs to be done fairly quickly to be useful. So we implemented a custom data structure to do this for us. And what this fuzz IP filter function does is it exercises this data structure, it builds it up with the block list based on the subnets that we get, and then it just checks for each of the IP addresses through our data structure, whether it's in the set. But it also just iterates over this vector of subnets and checks it explicitly whether the correct answer was given by our data structure. This turned out to be really useful in debugging this data structure. There were a couple of edge cases that I missed implementing the data structure originally. This thing found them within 30 minutes. So these are the kind of things where fuzzing, you might not think of the test case yourself, but if you can do these kinds of property checking, it'll find it for you. And that can be really, really useful. Those bugs would have been in our code today had I not written this fuzz test. So you might be a little bit wondering about why do we have specific types here. And that is because while the fuzzer library is very smart and it knows for most of the basic Rust types how to generate them from the arbitrariness that the fuzzer itself provides, it can't do everything, so we need to tell it how to generate our types. And that's basically done using something called the arbitrary trait. It's basically, it tells you how to go from some arbitrary data. The unstructured here is the arbitrary data. You tell it how do you generate now in our case, IP address. So we say, we take a Boolean, whether it's an IPv4 address or IPv6 address, and then we take some bytes, and we instantiate an address from that. It's usually, this is just plumbing code. It's really easy to write if you have some own types, and it allows the fuzzer then to do this for you. So in total, this fuzzer is about 60 lines of code. It took maybe 20 minutes to write, and it's really useful to have these kinds of capabilities. So we've got a number of other fuzzers in NTPD-RS, but these give a bit of a flavor of what is possible with fuzzing. Hopefully that is useful. I would, if you've never tried this kind of stuff, I would absolutely recommend go experiment with it. It can be really useful for finding bugs and issues in your code. A fuzzer will basically do things you wouldn't think of doing yourself to your code. It will break things, though. Be aware. So yeah, that's what I wanted to talk about to you today. Here are some useful URLs if you want to read up some more. The Rust Fuzz book is a really good introduction to how all this stuff works. It basically covers most of the ground I've covered here today, but it goes a little slower. If you are interested in our NTP implementation, want to play around with that, it's a GitHub project. And if you want more information just about the Proxima NTP project in general, you can also find it here. And that's all. Are there any questions?
After.
No.
I'm sorry to ask this because I'm very well aware of the great use that fuzzers have, but their opposite, the formal verification, is also something which may be used. Is there a better reason to use fuzzers than formal verification for this kind of stuff?
I've played around with formal verification in the past. My experiences with it have been that it's very much still a research project for a lot of things. It tends to put quite stringent requirements on how you write your code, which fuzzers basically don't. Fuzzers, the great thing about fuzzing over something like formal verification is a fuzzer basically can take what is there and just try to make it misbehave, and you don't really have to impose that much on the code that you write to be able to make use of that. So yeah, that's basically why we did not choose to use that.
It's a fair answer.
I mean, formal verification definitely has its uses, and if you go into the model learning stuff, I'm sure there is ways to do something useful, even for something like NTP. The cost-benefit analysis is a lot more difficult to make for formal analysis, particularly because the barrier for entry is so much higher. So for fuzzing, it's now basically as simple as writing a test these days for us, and that just there's at that point there's no good reason not to do it anymore.
Okay, what is the difference for you between fuzzing and property-based testing? Because when I used fuzzing, this was mostly coverage-guided fuzzing, so trying to increase code coverage with different samples. Does Cargo Fuzz implement that?
Yeah, so Cargo Fuzz is a coverage-based fuzzer. It will keep track of what it hits, tries to find inputs that hit new code paths. Property-based testing, I'm not really aware of what the exact formal definition of that is, I have to admit. I think technically some of the things I abuse Cargo Fuzz for these days could be classified as property-based testing, because I'm basically just saying this property should hold for this code, try to find me a counterexample. So I'm not sure how big that difference is. I must say I'm not that up to date on the latest research on property-based testing as well. I think there's also a formal methods approach to property testing, but to be honest, I've not seen that up close.
Kind of a follow-up question. Is there a way to save counterexamples as explicit tests to ensure that the property holds on afterwards?
Yes. So Cargo Fuzz, if it finds an input that breaks your code, it will provide you with the exact input how it did that. It does this through standard debug output, typically for Rust. If you use the standard outputs for that, it's very easy to convert that into an input that you could build a test around. We've done that specifically for the IP filter case. So some of these cases that broke my code, I've turned them into test later because I did not want to break my code that way again. And fuzz testing, it takes a little bit more time than normal tests, so it's nice to have the quick feedback for those.
Great, thank you.
Fuzz testing, basically you're lucky and the random number generator is going to hit your bugs. So tell us, how lucky have you been so far?
Well, it depends a bit on for us, the packet parsing, so far we've not found anything. Looking at the packet parsing code in NTP, I've got some reasons to assume that that's... oh, my laptop just crapped out with it. I'm guessing that's mostly because there are no things to be found there right now. That might change in the future. My experience so far has been that it converges to something stable relatively quickly. So I have fairly high confidence that for the fuzz test that we wrote, it found most of, if not all of what there was to find there. I think in total we found something like 5 or 6 different cases where something broke in a way it shouldn't. Yeah, it's not a replacement for manual testing. Usually you can, if you have a little bit of insight, you can write test cases that should exercise most of your system fairly quickly. But especially for finding the edge cases that you might have missed, it can be really useful, I think.
How long does such a test run? 5 minutes, 5 hours, a week?
It's up to you. Cargo Fuzz gives some feedback. I can show that if you want to. Let's do that. So I'll just start one live and hope that it doesn't find a bug. So can I zoom this easily in? Yeah, where? Ah, yeah, there we go. Cargo, nightly, fuzz list. I want to run the IP filter one. So that's It needs to build. This is a fairly fresh checkout of the code, so sorry, this will take a little while in the background. It depends a lot. So for the IP filter one, I think my original run was something like 2 hours. I think it was literally 5 minutes until it found the first crash. And my final run of it was a couple hours. A lot will depend on the complexity of your code. I would recommend, if you start playing around with this, start with small pieces of code first. Focus not on the whole of your application and write a fuzzer for that. Start simple, start with the smaller bits. It gives you easier test cases to debug. It runs faster. And it has, but you quickly see results from it that way. And then later on, you can always scale out to testing larger chunks of your application at once, if you're really interested in that. Oh God, clap. It's going to take a while. But it gives you some feedback on when it finds new paths, so we'll see that in a minute. If it'll, it's almost done. So yeah, it's still finding a lot right now because I don't have, this is a fresh checkout of code. So it's building up its thing basically again. So what you see here, every line with a new is basically, it finds a new way of exercising your code. Reduce means that it's found some way to make an input smaller. Turns out that that's useful to then more easily find new things. At some point, this will slow down. I'm not sure we have enough time to leave this running right now to see it slow down. And that's usually the point where if it finds no reductions or new things for a little while, that's usually when I cut it off. But yeah, you need to experiment with this. Longer is better with most fuzzers. And it depends a lot on how much code you're covering in one go. Any other questions in the meantime?
Mike's coming up. We still have 5 minutes for questions.
So I was wondering when it does find a counterexample, does it also try to find the smallest counterexample? So I think you just mentioned something about reducing, but
I think you can let it do that. I've not had a need for it yet.
Okay, so
So I don't actually have that much experience with that part. It tended to find relatively small counterexamples already for me, small enough that debugging by hand was perfectly possible. It is possible to tell it to do that. I know it's possible. I've never dove into the flags I need for that.
Yeah, so I think most property-based testing libraries have this as a feature, right? But I think they also need it more because they aren't as clever, I think, as this about what inputs or code paths they generate. Yeah. Okay. Thank you.
Question, but how does the fuzzer actually know it's wrong?
Okay, so the fuzzer really doesn't know that much. It basically observes one thing, and that's crashes. And if you want to check properties, just check in an assert in there, and Rust will make sure that it becomes a crash. And then at that point, the fuzzer is able to pick it up.
So it doesn't actually check if the output is correct. It just checks that it doesn't crash.
It checks that your code doesn't crash, but it has no way of knowing what correct means in your context. So depending on what you're testing, you either need to write something that will tell it, well, this code is probably doing something sensible, or you just accept that you're not going to find all classes of bugs with this. It's one of the reasons why fuzz testing is never the only thing you should be doing. You should always write explicit tests because, well, it's a random input, so who knows what the output should be. But if you know some properties that should hold for your output, for example, it should serialize back into the same byte stream, then it's something you can test quite easily. So you're seeing, by the way, it already slows down a little bit. It gives you some sense of how quick this kind of thing goes. This is not a really complex data structure that's just testing. This is about 200 lines of code that it's exercising. So, any other questions? that the final one, I think, given time?
Yeah. Final question. No pressure.
You showed us the code for actually implementing the arbitrary trait, and you say it was quite a run-of-the-mill, right? It's rather boring code, but
Yeah.
it's still looking at it makes you think, okay, this is so boring, I don't want to write this, right? Is it in any way derivable for arbitrary data structures?
For most things, I think it is. Arbitrary comes with a derive macro. Turns out for the specific case we had, it wasn't, due to restrictions on how standard library types work. I can't say the type arbitrary to implement this for them, and it's not implement this for all standard library types in the arbitrary crate itself. So I haven't played around with it, but I think for most structures it is able to just derive for you.
Cool, thank you.
Awesome, thanks a lot. And then